We're starting Unit 4 in this video, where we'll be talking about higher order polynomial functions. You remember that we've already talked about linear polynomials, which just means degree 1, quadratic polynomials, degree 2, and so in this unit, the higher order polynomials are really for referring to things with a power or a degree of 3, 4, 5, etc., something bigger than 2. As we normally do, we're going to start by taking a look at our functions, both analytically with a formula, as well as numerically and graphically. And I'm going to begin with the simplest form of a higher order polynomial, one that has just one term. We give this one actually a special name. We call it a power function when it's just a one-term polynomial like this, x to a power. And we are going to start by looking at x to the third and x to the fourth on this page from the numerical and graphical perspectives. So here we are with our y equals x cubed. If I plug negative 3 into that function, negative 3 cubed, negative times negative times negative, still negative. 3 times 3 times 3 is 27. So I get negative 27. Plugging in the negative 2, again, 3 negatives keeps it negative. 2 to the third power would be 8. Negative 1 cubed would be negative 1. 0 cubed is 0. 1 cubed is 1. 2 to the third power is 8. And 3 to the third power is 27. So let's go ahead and plot those points on our graph. Let's see here, the y-axis scale I believe is by 5s, 5, 10, 15, 20. Yeah, so those are going by 5s. So if I start with negative 3, negative 20, 25, 26, 27 would be about there. Negative 2, negative 8. Let's see, that would be 5, 6, 7, 8 around here. Negative 1, negative 1. 0, 0. 1, 1. 2, 8. And 3, 27. All right, and hopefully what you're seeing here is a graph that looks fundamentally different from anything we've seen so far. Certainly it doesn't look linear, too much curving going on for that. It's not a parabola. This is an entirely new type of function. And if I just kind of smoothly connect my dots here, get a function that looks like that. Okay. There's no real formal name for this shape, so I just kind of call it a little bit of a wavy function or a wave, just because I need something to call it later on when I start referring to it. So that's the graph of the x cubed function. Let's try one more. I'm going to try the x to the fourth function as well. So another power function, 1 degree higher. We'll start by plugging in our values again. Negative 3 to the fourth power. And just a real quick reminder, if you multiplied negative 3 by itself a total of 4 times, negative times negative is positive, another negative times negative is positive, so you're going to end up with a positive value here. 9 times 9 is 81, so this would be a positive 81. Negative 2 to the fourth power. Again, 4 negatives will make it positive. 2 times 2 times 2 times 2 is 16. Negative 1 to the fourth power will be a positive 1. 0 to the fourth power is still 0. 1 to the fourth is 1. Excuse me. 2 to the fourth is 16. And 3 to the fourth would be 81. Now, obviously the y values for the -3 and the +3 are really large. They're not going to fit in the graph I gave us. So I'm just going to plot this starting with the -2, 16. 5, 10, 15, 16, around there. Then I have -1, 1, 0, 0, +1, 1, and 2, 16. If you're starting to think, hey, this one looks a little bit similar to a parabola, I don't blame you at all. It does look quite similar to a parabola. The only thing is, right near the vertex, do you see how kind of flattened out that is? It's not technically a parabola, but the shape is similar to a parabola, just a bit more flattened near the vertex. Okay. So when we discuss these, just again to have names to call them, I mentioned that I'm going to refer to this as a wave. This one I'm just going to refer to as sort of parabola-like. It's not technically a parabola. Parabolas are only used for the quadratic functions, but it's parabola-like. And you can see that extra flattening near the vertex that's typical with an x to the 4th function. All right, well, I said we were going to investigate a pretty grand thing, right? All higher order polynomials. We obviously don't want to sit here and make more and more graphs. These take a little while to do by hand. So I'd like to now investigate some of the higher order polynomials, like x to the 5th, and x to the 6th, and x to the 7th. We've seen we can certainly plot them by hand, but let's speed up the process a little bit, and we'll use Desmos to graph some of the others. So that's where we're going with right now. We're going to plot some of these higher degree functions and just kind of see what we see. So I'm going to start with x to the 5th. That's the next one we haven't plotted. And you'll notice if you look at that, doesn't that look very similar to the x cubed graph? It's got that same kind of a wave. I was using a different window. I could replicate my window. I went from -4 to 4 on the x-axis. Somewhere like that. And I had gone from about -25 to 25 on the y. About like that. And so that's sort of similar to the window that I used over here. Oh, excuse me, you can't see that right now. Similar to the window that I had used on the paper. And again, you can see that the graph looks very similar to the x cubed graph. All right, I'm just going to keep adding graphs to the same grid. Let's do x to the 6th. Doesn't that one look an awful lot like x to the 4th? Parabola-like, but more flattened near the vertex? Huh. Well, let's try x to the 7th. Now we're back to that wave shape. And if you're already predicting x to the 8th, good for you. Make that one a different color. There it is, the orange x to the 8th. We're back to the flattened parabola shape, right? So what I'm hoping you're noticing here is that it seems the shape seems to depend on whether the power is even or odd. If I only look at the ones that had odd powers, and I could actually add my y equals x to the 3rd here as well that we did by hand, we can see that all of the odd power functions have this basically wave shape. Let's analyze that shape just a little bit. First of all, if I go back to my paper, we're saying if we had f of x or y equal x to the n where the degree was odd. All of the graphs looked very similar. They all looked like that. I will say that notice the x cubed is the least steep, then x to the fifth, then x to the seventh. So that kind of wave shape does get steeper the higher the power, but the overall shape doesn't really change. And again, I'm going to call this sort of a wave shape. All right, observed symmetry. This graph has a different kind of symmetry than what we've talked about before, right? We talked about symmetry across the y-axis, and this certainly doesn't have that. But it does have symmetry about the origin. Here's what that means. If you have a point here, xy, there's a symmetric point over here where the x is negative and the y is negative that's also on the graph. We actually didn't comment it on the time, but we saw it right in the table, right? If I have negative 2, negative 8, I also have positive 2, positive 8. Negative 1, negative 1, positive 1, positive 1. That kind of symmetry is called symmetry about the origin. And again, if the graph contains xy, it also contains minus x minus y. All right, as far as any sort of special points on the graph, something that might help us when we start to do our graph shifting, which we're going to do very soon, the one point I really want to draw your attention to is the point right here at the origin. Now, unlike a parabola that has a vertex, this doesn't have a vertex, right? There's no maximum, local maximum, or local minimum on this graph. But there is something interesting that happens there. Do you see how the graph is kind of curved downward on this side, but then it starts curving upward on that side? The name of that point is an inflection point. And it just means that that's the point where the graph changes the way it curves, from curving down to curving up in this case. So the special point that I want to be aware of is the inflection point, which is at the origin, 0, 0, where it goes from bending downward to bending upward. All right, let's talk next about the end behavior of the graph. This graph goes in opposite directions on the end, right? It goes down to the left, and it goes up to the right. All right, and last I want to analyze the intervals of increase and decrease. If I look at this graph, remember to read it from left to right. Starting over here on the left-hand side, we're going uphill, and we actually continue to go up all the way. So this is increasing everywhere. It increases from negative infinity to positive infinity. this graph has no intervals of decrease. It's not a decreasing graph anywhere. All right, so that takes care of all the odd powers. I'm going to go back to Desmos for a moment, and now we're going to go ahead and turn back on all the even powers. So I don't want to look at the odds anymore. I want to look at the even powers, x to the 6th, x to the 8th, and I can add the one we graphed by hand, x to the 4th. And again, you're going to notice that these all have the same basic shape. They all look like that kind of flattened parabola. Right? Again, you'll notice x to the 4th in red is not quite as steep as x to the 6th in blue. And then the x to the 8th in orange gets even steeper. So the higher the power, the sort of steeper the parabola is. Not parabola really, but the parabola-like function. But they all have the same basic shape. So these all have this basic look to them. And again, this is not an official name, it's just what I'm going to call it so we can talk about it, kind of like a flattened parabola. This one definitely has recognizable symmetry, right? This is definitely symmetric across the y-axis. You have the mirroring going on both sides. And I don't know that we've actually formally talked about it this way before, but notice that what that means is if there's a point xy here, then there's a point on the other side where the x value is negative, but it has the same y value. So I could say if the graph contains xy, it also contains minus xy. And again, if I go back to the table we made, look, for example, at the positive 3 and the negative 3. They both have the same y value. Positive 2 and negative 2, they both have the same y value. Right? So we see that in our table as well. All right, special points in the graph. This one we're pretty used to. This, just like a real parabola, does have a vertex, a local minimum, and the end behavior of my graph, both ends go up. So up to the left and up to the right. All right, this one does have both increasing parts and decreasing parts. So let's take a look back here again. I'll notice that the graph is going, read from left to right, it's going downhill until I get to the vertex. So from negative infinity to 0 on the x-axis, the graph goes downhill. So decrease would be from negative infinity to 0. And then on the other side, whoops, sorry. On the other side, we have the increasing here. So from 0 to infinity, we would have an increasing graph. All right, well, we spent quite a bit of time and energy looking at these two types, the even powers and the odd powers. But where that's really going to pay off is now I can apply the same exact ideas that you did with quadratics or parabolas in terms of shifting these things. These have very predictable responses to certain algebraic changes. So that's what we're going to look at here on the next page. Now that we've got a really pretty good idea of what these graphs of power functions look like, we've done a pretty thorough analysis, we're going to consider how modifying the equation of a power function will change that graph in a predictable way. In order to do this, just a reminder, is this familiar quadratic function a power function? It is, right? It's x to a power. Fits the definition. Since it does, it makes sense that the same transformations that we use to help us graph different versions of our x squared are still going to work for any power function. And in fact, we'll see throughout the course, actually any function at all. So in this table, we are going to look at our power functions with specific algebraic changes. Right? These are written out for the x squared, so these are familiar. We're going to write them out generally for any power function. And then I've written out for you the most general form for any function at all. So first of all, oh, by the way, notice that I'm assuming a, h, and k are positive values here. When we had our parabola, our true parabola, and we put a multiplier in front of it, that was a vertical stretch or a vertical shrink, right? Stretch was for a bigger than 1. Shrink was for a smaller than 1. That is still going to work when I have any power of x. So if I were to write f of x equals ax to the n, for n odd, I would have the wavy function with a vertical stretch or shrink. And for any even n, I would have the flattened parabola with a vertical stretch or shrink. In general, that works for any function. If I make a new function by taking an old function and multiplying it by a constant, the relationship between the graphs is always a vertical stretch or shrink. All right, what happened when we put a negative in front of our x squared? That turned it upside down, right? Or reflected it across the x-axis. And again, that doesn't just work for parabolas. It works for any power function. So if I made my f of x equal to minus x to the n, it would take the wavy shape, turn that upside down. It would take the parabola, flattened parabola, turn that upside down. It works for any power function. And in fact, it works for any function in general. If I put a negative in front, my new graph will just be the reflection across the x-axis of the old graph. All right, what happened when we had x plus h squared? We're adding something to x before we square it. Remember how that graph moved to the left by h units? That's not just true for parabolas. It's also true for any power function. So if I have x plus h to the n, which is either the wave or the flattened parabola, it will move that left h units. And again, that actually works for any graph. If you replace x with x plus h, it moves the whole graph left h units. If I have x minus h instead, then we move to the right. And again, that works for any power function. And in fact, works for any function in general. These are the ones we called the horizontal shifts because they're moving left and right. All right, our last two. What if we add or subtract after we square the x? Those were the vertical shifts, right? Up and down. This one would go up k. This one would go down k. We looked at it specifically for parabolas before, but again, it works for any power function. So if I have a power function x to the n plus k, or a power function x to the n minus k, the shift is still going to be up or down. And again, that works for absolutely any function. And again, these we were calling the vertical shifts, up and down. All right, so we are ready to do a little graph shifting. We're going to try and sketch each graph using the transformations, and then we'll fill in the information in the table. So I'm going to start here by saying, let's think about what the parent function would be. Since this is a fourth power, I'm thinking my parent function would just be y equals x to the fourth before all the transformations were in place. And just for my own memory, it's an even power, so I know it would graph as kind of that flattened parabola. Right. Oops, and you know what? I'm sorry. There was a space for me to put that in the boxes down here. Let me do that. All right. Now we'll talk about what transformations have occurred. The negative in front reflects it across the x-axis. And then inside the parentheses, I'm subtracting 3 from the x before I raise it to the power. So that's a horizontal shift. That would be to the right 3. So I'm going to think the special point on these is the vertex. And I'm going to go ahead and I'm going to do the shifting, and then I'll write down what the vertex is in this particular case. So let's go right 3, reflect across the x-axis, and sketch. So right 3 brings my vertex over here, and then I'm going to go with that flattened parabola, but reflected across the x-axis, so upside down. Just like with past graph shifting, I'm not expecting a perfect graph here. I'm not real worried about the exact y values here. I just want that special point, that vertex in the right spot. I want the upside down, and I want the basic shape. So my new vertex here is going to be at 3, 0. All right, intervals of increase. This graph actually starts out increasing, and it continues to increase until I get to the vertex, where x is 3. So from negative infinity to 3, my graph is increasing. As far as intervals of decrease, my graph decreases starting from 3 forevermore. So from 3 to infinity, I have that decreasing graph. All right, domain and range. We haven't talked about those with our power functions yet, but we're pretty used to reading those off a graph, so we should be good to go here. The domain, this goes slightly to the left forever and slightly to the right forever. So just like the quadratics, my domain's going to go from negative infinity to infinity. This is still going to be just sort of a gimme. Negative infinity to infinity for really all power functions. As far as the range, though, this does go down to negative infinity, but the y values don't get any bigger than 0. So the range would go from negative infinity to 0. All right, let's try a couple more. We've got another shifted power function here, and with a third power, I'm thinking that my parent function is y equals x cubed. Right? I know because of the odd power, that graph is one of the waves. Looks like that, right? All right, as far as transformations, inside the parentheses, I have my horizontal transformation, so that's left 4, and outside is the vertical, down 2. Left 4, down 2. With the wavy graph, it's the inflection point that's the special point. So I'm going to take the inflection point from the origin and shift it left 4 and down 2. Now let's see, the vertical axis is by 2s, 2, 4, 6, 8, 10. So left 1, 2, 3, 4, down 2 would actually put me right there. All right, this one has not been flipped upside down or anything, so I'm just going to graph the same shape, assuming that's my inflection point. So it curves up on this side, and it curves facing down on that side. Again, I don't need anything other than that shift and the basic shape. That's all I'm looking for. My new special point, which in this case is the inflection point, has now moved to negative 4, negative 2. All right. As a wave, this is always increasing. So my interval of increase is everything from negative infinity to infinity. And I don't have any part of this graph that's decreasing. This graph goes forever left and right, and it also goes forever down and up. So both the domain and range this time will go from negative infinity to infinity. All right, I've got one more for us to try. We have minus x to the 5th plus 6. So first of all, I'm going to notice the 5th power, meaning my parent function is y equals x to the 5th. And with the odd power, that's going to be one of the wavy shapes again. In terms of transformations, there's a negative multiplier. So this one's going to be reflected across the x-axis and then up 6. The special point for the waves is the inflection point, which was at the origin. I'm going to take it from there and I'm going to move it up 6. So 2, 4, 6 right there. My new inflection point is at 0, 6. All right, the last thing I need to think about is when I draw this now, it needs to reflect, or in other words, get flipped upside down. So instead of going down this way and up that way, it's going to be the opposite, right? It's going to be up on this side and down on that side of the inflection point. So on this side, it curves up, and on this side, it curves down. Same shape, just upside down. All right, so that's my graph. Again, that's as accurate as I need it for this purpose. And you'll notice that this one, because it got turned upside down, is always decreasing. So this time there are no intervals of increase, and it decreases everywhere from negative infinity to infinity. Domain and range goes left and right forever, goes up and down forever, negative infinity to infinity for both of those. All right, so that brings us to the end of 4.1, looking at our power functions. For the rest of this unit, we'll actually be looking, kind of basing things a lot on these power functions, but we'll start combining them, adding and subtracting them to create full polynomial functions.